Welcome! In today's session, we'll tackle an interesting coding problem titled Shortest Distance to Target Color. We'll break down the problem, explore different approaches, and analyze their complexities. Let's dive in. In this problem, you are given an array called colors, where each element represents the color of a house. The color is denoted by an integer, specifically 1, 2, or 3. Additionally, you are provided with a list of queries. Each query consists of two values, an index, which represents the position of a house in the colors array, and a target color, which is the color you want to find the shortest distance to. The goal is to determine the shortest distance from the house at the given index to any house with the specified target color. If no house with the target color exists in the array, the result for that query should be -1. The distance between two indices I and j is calculated as the absolute difference, abs, ij. The problem constraints make it clear that the colors array can be large, up to 10⁻5 elements, and there can be as many as 10⁻4 queries, so efficiency is key when designing a solution. The solution to this problem should return an array of integers, where each element corresponds to the shortest distance for a specific query. If the target color does not exist in the array, the result for that query should be -1. Let's look at an example. Suppose the colors array is 1, 1, 2, 1, 3, 2, 2, 3, 3, and the queries are 0, 3, 4, 2, 8, 1. For the first query, we are looking for the shortest distance from the house at index 0 to any house with color 3. The closest house with color 3 is at index 4, so the distance is abs, 0 to 4 equals 3. Thus, the result for the first query is 3. For the second query, we are looking at index 4 and searching for the nearest house with color 2. The closest house with this color is at index 5, so the distance is abs, 4 to 5 equals 1. The result for this query is 1. For the third query, we are at index 8 and need to find the closest house with color 1. The nearest house with color 1 is at index 3, which gives a distance of abs, 8 to 3 equals 3. The output array for this example is 3, 1, 3. Now, consider another example with colors equals 1, 2, 3, 2, 1, 3, 3, and queries 3, 1, 2, 2, 6, 3. For the first query, the closest house to index 3 with color 1 is at index 1, so the distance is abs, 3 to 1 equals 2. For the second query, the house at index 2 already has the color 2, so the distance is abs, 2 to 2 equals 0. For the third query, the house at index 6 already has the color 3, resulting in a distance of abs, 6 to 6 equals 0. The output for this example is 2, 0, 0. Finally, let's consider an example where the colors array is 1, 1, 1, 1, 1, and the queries are 0, 2, 2, 3, 4, 1. For the first query, we are looking for color 2, which does not exist in the array, so the result is -1. Similarly, for the second query, we are searching for color 3, which also does not exist, so the result is again -1. For the third query, we are already at a house with color 1 at index 4, so the distance is abs, 4 to 4 equals 0. The output for this example is -1, -1, 0. These examples highlight important edge cases, such as when the target color is missing entirely from the array or when the required house is at the same index as the query. The constraints emphasize the need for an efficient solution, as the array and query sizes can both be large, and redundant computations should be avoided wherever possible. To solve the problem of finding the shortest distance to a target color, one approach we can consider is the brute force method. The intuition here is straightforward. For every query, we iterate through the colors array and look in both directions, left and right, from the queried index. We calculate the distance to the nearest occurrence of the target color and keep track of the smallest distance found. The steps are simple. For each query, we initialize the minimum distance to infinity, traverse the array in both directions from the given index, and record the shortest distance once we find the target color. While this method is easy to understand, it has significant drawbacks. The time complexity is n*q, where n is the length of the colors array and q is the number of queries. This inefficiency arises because we may end up traversing the array repeatedly for each query, leading to redundant computations. Moreover, the space complexity is O(1), as we don't use any additional data structures. However, this approach is not practical for large datasets, as the repeated traversal of the array makes it computationally expensive for a high number of queries. A more efficient solution involves pre-processing the colors array to optimize the query responses. The key idea is to pre-process the array and store information about the closest indices for each color at every position. This eliminates the need to recompute distances for every query. The process relies on two key observations. First, we can maintain the nearest index of each color while traversing the array, and second, by performing two passes, one left to right and one right to left, we can calculate the shortest distances to any color in both directions. Specifically, we create a dictionary where nearest, C, I, holds the shortest distance to color C at index I. In a left to right pass, we update the nearest indices as we encounter each color. Then, in a right to left pass, we refine these distances to ensure the nearest index is captured from both directions. Once pre-processing is complete, answering a query becomes a simple lookup in the pre-computed dictionary, which takes constant time. This approach significantly reduces redundant computations and ensures efficiency. With pre-processing complete, the optimized approach achieves a time complexity of O, n plus q. The pre-processing step involves two linear passes through the colors array, which takes O, n, and each query is answered in O, 1, by simply looking up the pre-computed value. The space complexity is O, n, as we store distances for each position in the array. This method is highly efficient, especially for scenarios with large arrays and a high number of queries. The chosen strategy is the optimized approach because it balances the pre-processing overhead with query efficiency, making it scalable and performant. While the pre-processing step adds some initial computation time, this is negligible compared to the gains during query resolution. The trade-offs include the additional memory used for storing pre-computed distances, but this is manageable given the linear space requirement. Overall, the optimized approach is preferred for its ability to avoid redundant computations and its scalability, making it the best choice for handling large datasets with numerous queries. In this problem, we are tasked with determining the shortest distance from a given index in an array, called colors, to the nearest index that contains a specified target color. The challenge lies in efficiently handling multiple queries where each query specifies an index and a target color. To begin, we can consider a brute force solution using naive iteration. Here, the idea is straightforward: loop through the colors array for each query to find the nearest occurrence of the target color. The steps are as follows. First, parse the input, which includes the colors array and the list of queries. For each query, initialize a variable min_distance to infinity. Then, iterate through the colors array, checking each index to see if the color matches the target color. If it does, calculate the distance using the absolute difference between the current index and the query index. Update min_distance whenever a smaller distance is found. If no matching color is found after iterating through the array, return -1 for the query. Otherwise, store the smallest distance and repeat the process for all queries. Finally, return the results as a list. While this approach is simple to implement, its inefficiency for large inputs makes it impractical as the array size and query count grow. The brute force approach, while intuitive, has a significant drawback: it operates with a time complexity of O, n*q, where n is the size of the colors array, and q is the number of queries. This can become computationally expensive for large inputs, such as when both n and q are in the range of 10,000. To optimize the solution, we can take advantage of the fact that the colors array is static, meaning it does not change between queries. By pre-processing the array, we can reduce the repeated work and improve efficiency. The optimized approach involves pre-computing the shortest distances for each color to all indices in the array. This allows us to answer each query in constant time. The pre-processing begins by creating a dictionary called distance_map. This dictionary stores the shortest distances for each color as a list, where each index corresponds to the distance to the nearest occurrence of that color. To populate this map, we perform two scans of the colors array. The first scan goes from left to right, tracking the last seen index for each color and updating the distances as we iterate. This ensures that the distances are correct for indices where the nearest occurrence is to the left. Next, we perform a second scan from right to left, which updates the distances for indices where the nearest occurrence is to the right. With this pre-processing step, we significantly reduce the computational overhead during query processing. After the pre-processing step, we can efficiently process the queries. For each query, which consists of an index and a target color, we simply retrieve the pre-computed distance from the distance_map. If the target color does not exist in the dictionary, we return -1 for that query. Otherwise, we retrieve the stored shortest distance directly. Once all queries are processed, the results are returned as a list. To implement this approach, we rely on specific data structures. The colors array stores the input data. The distance_map dictionary efficiently maps each color to its corresponding list of pre-computed distances. Finally, a separate list is used to store the results for each query. When analyzing the complexity of this solution, the pre-processing phase involves 2 scans of the colors array for each unique color. If there are distinct colors, the pre-processing takes (n) time. Query processing, on the other hand, is highly efficient. Retrieving a pre-computed distance takes (1) time per query, and for Q queries, this totals (Q). Thus, the overall time complexity is (n plus Q). In terms of space complexity, the distance_map requires (n) storage, which is manageable given the constraints. When implementing any algorithm, it is important to consider edge cases to ensure robustness. For example, if the target color does not exist in the array, the algorithm should return -1 for those queries. Additionally, while the problem guarantees valid indices, it is good practice to handle out-of-bound indices gracefully. For a single element array, the implementation must avoid unnecessary computations while still producing correct results. Lastly, when multiple queries request the same index and target color, the pre-processing ensures that these queries are handled efficiently without redundant calculations. To illustrate the optimized approach, let's walk through an example. Consider the input colors equals 1, 3, 2, 3, 1, and the queries 2, 3, 0, 1, 4, 2. During pre-processing, we perform a left-to-right scan. For color 1, the distances are initially 0, INF, 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 0. For color 3, they are INF, 1, 0, 0, INF, and for color 2, INF, INF, 2, INF, INF. Next, the right-to-left scan updates these distances. For color 1, the distances become 0, 4, 2, 1, 0, and similar updates are made for the other colors. This pre-processing ensures that the shortest distances are available for all indices and colors. Using the pre-computed distances, we can now process the queries. For the first query, 2, 3, the distance to the nearest 3 from index 2 is 1. For the second query, 0, 1, the distance to the nearest 1 from index 0 is 0. Finally, for the query, 4, 2, the distance to the nearest 2 from index 4 is 2. Collecting these results gives the output 1, 0, 2. This example demonstrates how pre-processing allows us to answer each query in constant time, making the algorithm efficient even for large inputs. By leveraging pre-computed data, we avoid the inefficiencies of the brute force approach and achieve a significant improvement in performance. To solve the shortest distance to target color problem, we begin by pre-processing the input data. Here, we use a defaultic to create a mapping where each key is a color, and the value is a sorted list of indices representing the positions of that color in the input array. This pre-processing step allows us to efficiently look up the indices of any given color later. We iterate through the colors list using enumerate, which gives us both the index and the color at that index, and we append each index to the corresponding colors list in the defaultic. Following this, we define a helper function called find_closest_index to determine the closest index to a given target using binary search. The binary search approach minimizes the search space by repeatedly halving it until the closest index is found. Inside the function, we initialize pointers for the left and right bounds and calculate the midpoint in each iteration. Depending on whether the midpoint value is less than or greater than the target, we adjust the pointers accordingly. After the binary search loop completes, we check both the left and right neighbors to ensure we find the minimum possible distance to the target index. This is achieved by comparing the absolute differences between the target and the indices at the left and right bounds, returning the smallest distance found. Now that we have our pre-processing and helper function ready, we move on to processing the queries. Each query provides an index and a target color, and we need to find the shortest distance to any occurrence of the target color from the given index. We start by initializing an empty result list to store the output for each query. For each query, we first check if the target color exists in our color_indices mapping. If it doesn't, we append -1 to the result, indicating that the color is not present in the input. Otherwise, we use our find_closest_index helper function to find the shortest distance to the target color. This function takes the sorted list of indices for the target color and the current index as inputs. The closest distance returned by the helper function is then appended to the result list. After processing all queries, we return the result list, which contains the shortest distances for each query. This approach ensures an efficient solution by leveraging pre-processing and binary search to handle potentially large inputs in query sets. Here, we start by importing the necessary Java utilities and defining our solution class. The main method, shortestDistanceColor, takes two inputs, an array colors that represents the colors at each index and a queries array where each query specifies an index and a target color. The first step in solving this problem is pre-processing the colors array. We use a hash map to map each color to a sorted list of its indices. This allows efficient access to the positions of any color in the array. As we iterate through the colors array, we populate this map using the computeIfAbsent method, which ensures that each color key is associated with a list. If the key doesn't exist yet, it initializes a new array list for that color and then appends the current index. Next, we define a helper function, findClosestIndex, which implements binary search to determine the nearest index of a specified color. Within this function, we use a standard binary search approach, adjusting the left and right pointers based on the midpoint value. Once the binary search concludes, we calculate the closest distance by comparing the indices near the binary search result. If the left pointer is still within bounds, we check the distance to that index and keep track of the minimum distance found so far. If the right pointer remains within bounds, we similarly calculate the distance to that index and update the minimum distance accordingly. This ensures that we always return the closest index to the target, regardless of whether it's to the left or right of the given position. With the pre-processing and helper function in place, we then process each query in the queries array. For every query, we extract the target index and the target color. If the target color isn't present in the color indices map, we add -1 to the result list, indicating that the color is not found in the array. Otherwise, we retrieve the list of indices for the target color and use the findClosestIndex function to compute the minimum distance to the specified index. This distance is then added to the result list. Finally, after processing all the queries, we return the result list, which contains the shortest distances for each query. This implementation efficiently handles the problem by leveraging pre-processing and binary search, ensuring optimal performance even for large inputs. To solve the problem, we start by pre-processing the colors array. The goal here is to group all indices of the same color together for efficient lookups. Using a default dict, we iterate through the colors array and store the indices of each color. For the input colors equals 1, 1, 2, 2, 3, 3, this results in color_indices equals 1, 0, 1, 2, 2, 3, 3, 4, 5. Now, moving to the first query, 0, 1, this asks for the shortest distance to color 1 from index 0. Looking at the indices for color 1, which are 0, 1, we use binary search to find the closest index to 0. In this binary search, with left equals 0 and right equals 1, the midpoint is mid equals 0, or indices, mid, equals 0. Since this matches the target or is less than it, we move right to -1. The nearest index is therefore indices, 0, equals 0, and the distance is simply abs, 0 to 0, equals 0. So, the result for this query is 0. Now, let's process the second query, 3, 3, which asks for the shortest distance to color 3 from index 3. From our pre-processed color_indices, we see that the indices for color 3 are 4, 5. Using binary search, we aim to locate the closest index to 3. With left equals 0 and right equals 1, the midpoint is mid equals 0, or indices, mid, equals 4. Since 4 is greater than the target index 3, we move right to -1. At this point, we check the nearest indices. The left pointer is at 0, so the distance to indices 0 equals 4 is abs, 4 to 3 equals 1. This gives us the shortest distance of 1. Thus, the result for this query is 1. Combining both queries, the final output becomes 0, 1. In the next example, we consider a scenario where a queried color is missing from the colors array. For the input colors equals 1, 2, 3, 4, and queries equals 2, 5, 3, 4, our first step is to pre-process the colors array. By grouping the indices of each color, we get color underscore indices equals 1, 0, 2, 1, 3, 2, 4, 3. The first query, 2, 5, asks for the shortest distance to color 5 from index 2. However, color 5 is not present in our color underscore indices dictionary. Since the color doesn't exist, the answer for this query is -1, indicating that no valid distance can be calculated. For the second query, 3, 4, we are tasked with finding the shortest distance to color 4 from index 3. From our preprocessed data, the indices for color 4 are 3. Using binary search, with left equals 0 and right equals 0, the midpoint is mid equals 0, or indices, mid, equals 3. This is an exact match to the target index 3. Therefore, the nearest index is 3, and the distance is abs, 3 to 3, equals 0. The result for this query is 0. Combining the results from both queries, the final output for this example is -1, 0. In this example, we handle a case where there are multiple closest indices for a color. Given the input colors equals 1, 1, 1, 2, 2, 3, and queries equals 4, 1, 5, 2, we first preprocess the colors array. Grouping indices by color, we obtain color underscore indices equals 1, 0, 1, 2, 2, 3, 4, 3, 5. For the first query, 4, 1, we need the shortest distance to color 1 from index 4. The indices for color 1 are 0, 1, 2. Using binary search, we start with left equals 0 and right equals 2. The midpoint is mid equals 1, where indices, mid, equals 1. Since this value is less than the target index 4, we move left to 2. Now, with left equals 2 and right equals 2, the midpoint is mid equals 2, where indices, mid, equals 2. Again, this is less than the target, so we move left to 3. At this point, we check the nearest index on the right, which is indices, 2, equals 2. The distance is abs, 2 to 4, equals 2. So, the result for this query is 2. For the second query, 5, 2, we want the shortest distance to color 2 from index 5. From our preprocessed data, the indices for color 2 are 3, 4. Using binary search with left equals 0 and right equals 1, the midpoint is mid equals 0, or indices, mid, equals 3. Since this value is less than the target index 5, we move left to 1. Now, with left equals 1 and right equals 1, the midpoint is mid equals 1, where indices, mid, equals 4. This is still less than the target, so we move left to 2. At this point, we check the nearest index on the right, which is indices, 1, equals 4. The distance is abs, 4 to 5, equals 1, giving us the shortest distance of 1. The result for this query is 1. Combining the results, the final output for this example is 2, 1. To analyze the time complexity of this solution, we break it into two main steps, pre-processing the colors array and processing the queries array. During pre-processing, we construct the color underscore indices dictionary. This involves iterating once through the colors array, which has a size of n. Each index in the array is appended to the list corresponding to its color in the dictionary. Since we process each index exactly once, this step takes n time. Now, for query processing, each query involves 3 substeps. First, checking if the target underscore color exists in the dictionary is a constant time operation, 1, thanks to the efficiency of dictionary lookups. Next, we perform a binary search on the list of indices for the target underscore color, which takes log m, where m is the size of that list. Finally, determining the closest distance involves only a few constant time calculations, so it contributes 1 time. Together, these substeps allow us to efficiently answer each query. Now, since there are q queries, and each query involves operations that take log m time, the total time required for processing all queries is q*log m, where M is the average size of the lists in the color underscore indices dictionary. Combining this with the pre-processing step, we get the total time complexity of the solution. Pre-processing takes O, N, and query processing takes O, Q asterisk log M. Therefore, the overall time complexity is O, N plus Q asterisk log M. This balanced combination makes the solution efficient even for larger inputs, as both the pre-processing and query handling steps scale well. Let's now focus on the space complexity of the solution. During pre-processing, we store the color underscore indices dictionary. This dictionary maps each unique color to a list of indices where that color appears in the colors array. In the worst case, each index in the array corresponds to a unique color. This means the dictionary could grow to a size of O, N. Additionally, the binary search helper function only requires a constant amount of extra space for pointers like left, right, and mid, which means it uses O1 auxiliary space. The result list, which stores the shortest distances for all Q queries, contributes an additional O-Q space. Combining these factors, the total space complexity of the solution is O, N plus Q. This balance ensures that the optimized solution remains memory efficient while handling large inputs. To better understand the efficiency of the optimized solution, let's compare it to a naive approach. In a brute force solution, each query would involve iterating through the entire colors array to find the closest index with the target color. Since there are Q queries, this approach would take O, Q asterisk N, time. In contrast, the optimized solution pre-processes the colors array to create the color underscore indices dictionary. This allows each query to leverage binary search on pre-computed lists, reducing the time complexity of each query to O log M, where M is the average size of the lists in the dictionary. Thus, the total time complexity becomes O, N plus Q asterisk log M, which is significantly faster than O, Q asterisk N, for larger inputs. However, the optimized solution does require additional pre-processing space, O, N, for the dictionary, whereas the brute force approach uses no extra space. Despite this trade-off, the drastic improvement in query time complexity makes the optimized solution far more suitable for scenarios with large datasets. Let's examine how the solution performs in different scenarios. In the best case, all queries target colors that are extremely rare, meaning the lists in color underscore indices are very small. Here, the binary search step is exceptionally fast, and the total time complexity remains O, N plus Q asterisk log M, where M is minimal. In the worst case, all queries target colors that are very common, resulting in large lists for those colors. In this scenario, binary search takes longer as log M approaches log N when M is close to N. Still, the overall time complexity remains O, N plus Q asterisk log M. For the average case, where colors and queries are more evenly distributed, the list sizes are generally smaller than N. This keeps the average time complexity close to O, N plus Q asterisk log M, making the solution efficient across a wide range of inputs. By balancing pre-processing and query efficiency, the solution ensures robust performance in diverse scenarios. Let's talk about some common mistakes to avoid when solving this problem. One of the biggest pitfalls is using inefficient iteration for every query. Many brute force solutions involve retraversing the entire colors array for each query, leading to an O, N asterisk Q, time complexity. This approach doesn't scale well for large inputs. Instead, focus on pre-processing the data to minimize redundant computations. Another issue arises when people overlook edge cases, such as when the target color doesn't exist in the colors array. You should handle this by returning a clear indicator, like -1. Then there's the problem of handling multiple closest houses. If two houses are equidistant, your solution must correctly return the closest valid house, not an arbitrary one. Improper pre-processing can also be a problem. For example, storing redundant indices for every color can lead to excessive memory usage. Instead, use efficient data structures like dictionaries or sparse arrays. Finally, binary search is a powerful tool here but can be tricky to implement. Watch out for off-by-one errors in edge cases, such as when the target falls outside the range of available indices. Now, let's consider some insights for interviews. First, this problem highlights the importance of recognizing patterns. It's a classic example of pre-processing for efficient query handling. Many problems involving repeated queries benefit from pre-processing, so identifying this pattern early can save time. Additionally, be prepared to discuss trade-offs. For instance, pre-processing might require O(n) or O(n*k) time and space, but it significantly improves query efficiency to O(1) or O log n. Interviewers also appreciate candidates who can present multiple approaches. Explain the brute force method, but also discuss optimizations like binary search or the sliding window technique. Lastly, always demonstrate awareness of edge cases. For example, if a query requests a color not present in the array, clarify how your solution handles it. Asking these kinds of questions shows that you're thinking critically about constraints and requirements. This problem also connects to several related problems on LeetCode. For example, problem 1838, frequency of the most frequent element, involves optimizations using the sliding window technique. Problem 1090, largest values from labels, focuses on handling constraints with efficient pre-processing. Problem 2080, range frequency queries, is all about efficient range query handling, and problem 1980, find unique binary string, emphasizes edge case handling and efficient lookups. In terms of alternative approaches, one option is pre-processing with dictionaries. Here, you store the indices of each color in a dictionary, and for each query, use binary search to quickly find the closest house. This method balances pre-processing time and space at O(n), while each query runs in O log n. Another approach involves using a two-pointer sliding window. By maintaining a dynamic window for the closest house of each color, you can efficiently update the window as you traverse. This method is especially useful for ordered queries, though it's less effective for arbitrary queries. Another pre-processing technique involves creating a 2D array that pre-computes the closest house for each color at every index. This indexed pre-processing allows you to answer queries in constant time, O(1), but comes at the cost of O(n*k) space complexity. It's a trade-off worth considering for scenarios with many queries. Of course, you could also use the brute force approach, which involves checking all possible houses for every query. While this method is simple to implement, it's highly inefficient, with a time complexity of O(n*q). It's generally not suitable for larger inputs, but it can be a good starting point for understanding the problem before diving into optimizations. Great job! Today, we explored the shortest distance to target color problem, analyzed its solution, and extracted key takeaways. Remember, practice makes perfect. Thank you for joining, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!